Welcome back to the second part of Lecture 5 of our course, Introduction to Complex and Algebraic Geometry. So in part 1 of Lecture 5, we started discussing higher dimensions in the world of complex numbers. We are going to do a quick review and continue with the definition of holomorphic functions in higher dimension. So as a very quick review, let's remember that in the world of real numbers, we would think about R, just a set of real numbers, as a real line, as a one-dimensional object, right? We would think about R2, the flat plane, as two-dimensional real object, two-dimensional real vector space. R3 as three-dimensional, and we could think about Rn for any positive integer n as an n-dimensional real vector space. We learned there's a complex analog of that. The set of complex number, although as a real vector space is two-dimensional, as a complex vector space is one-dimensional. So when we think about it as a complex vector space, C is just C to the 1, and it's a one-dimensional complex space. In the same way, we could think about C2, which is as a real vector space, R2 times R2, which is R4. So as a real vector space, it's four-dimensional, but as a complex vector space, it's two-dimensional. And we learned in the same sense, we can define Cn to be the set of points, Z1 up to Zn, where each Zj here from Z1 to Zn is a complex number. As a complex vector space, it's n-dimensional. As a real vector space, it's just R to n, so it's 2n dimensional. That's the first thing we learned. Then we learned in the same way that we can, for a complex number z, we can always write it as a real number x plus I, y. Now that we have points of the form z1 up to zn as an element in Cn, each of these complex numbers, each zj can be written as a real number, say xj, plus the imaginary number I, another real number yj. So any point z1 up to zn is kind of corresponds to a point denoted by x1, y1 up to xn, yn, a point in R to n, right? So this is a correspondence between one-to-one correspondence between Cn and R to n. Okay, so that's the first thing we learned. The second thing we learned was that just as in calculus, where we started by studying functions from R to R, and in calculus at some point we get to higher dimensions and we study functions from, say, Rn to Rm, and then we study differentiability, continuity, and properties of these functions defined in higher dimensional real vector spaces. You could think about the same thing happening in the world of complex numbers. So in this course, we studied what does it mean for a function to be complex differentiable when it's a function from C to C, or maybe defined on an open subset inside C, or what it means for such function to be holomorphic or analytic, etc., right? It makes sense to study the same properties when the domain and target are higher dimensional vector spaces. So we can think about functions from Cn to Cm for two positive integers n and m, and say, what does it mean for such function to be holomorphic or analytic or complex differentiable, etc. That's what we want to do. So we want to see when we would say a function f from Cn to Cm is, say, complex differentiable or holomorphic. So let's take a look at that. Let's think about that for a second. So if we have a function f from Cn to Cm, the input is from Cn. So the input is an n tuple of complex numbers z1 up to Zn, right? And f of that is supposed to be a point in Cm. So f of any such thing for a given z1 up to Zn would be something in Cn. So it should have m components. So there would be the first component. We denote the first component by f1 of these points, z1 up to Zn. And then there would be second component, etc., until we get to the last component, which would be Zm. Now, each component, each fj, where j is any number between any integer between 1 and n, each fj itself can be understood as a function from Cn to C, right? It's just one component of our function, right? So most properties of functions are defined component-wise, in the sense that I would say this function is continuous. You can think about it maybe as a theorem, but anyways, or differentiable if each component, if each fj is continuous or differentiable. So it makes sense first to study functions which their domain is higher dimensional, but their target is one-dimensional, because any property I like to define for f, say being differentiable or continuous, implies each component should be such. So it makes sense first to consider each fj where the target is one-dimensional. It's just C. So I would drop j and we start by studying functions which are defined on Cn to C, or maybe an open subset inside Cn to C, and say what it means for such function to be complex differentiable, what it means for this function to be holomorphic or analytic, etc. So that's the main question we want to address. Before going there, again, let's recall another thing we learned. So we learned for functions f from C to C, we have three different notions of differentiability when working with complex numbers. One was we would say f is complex differentiable at a given point, say z naught, if this limit, when h goes to 0, if this limit exists, right? Where h here going to 0 is a complex thing. It can go to 0 along any path in the set of complex numbers. If this thing exists, we would say this is the derivative of f at z naught, complex derivative of f at z naught, and it's complex differentiable there. And if it exists, this limit exists for any point in the domain, the function is complex differentiable in its domain. We had a second definition, we would say f is holomorphic if it's differentiable in the real sense and it satisfies the Cauchy-Riemann equation, right? We would say it's holomorphic if it satisfies the Cauchy-Riemann equations, which in the complex form, they can be summarized as partial derivative of f with respect to z bar vanishes, plus some regularity. And then we had the notion of analytic. We would say a function f is analytic if locally it can be given as an infinite sum. So f of z can be written as sigma a n, z minus some z naught to the n, where n goes from 0 to infinity for some z naught. And on some domain, this would be uniformly convergent. We can do this everywhere. We would say the function is analytic. And we learned essentially all these properties are equivalent with a little bit of assumption. Now let's see if we can extend these things to higher dimension where the domain is not C, but it's some Cn, right? How can we generalize these definitions to higher dimensions? So let's look at the first definition, complex differentiable. If you were to just write the exact same thing as the limit, it would not make sense in a naive sense. So let's say naively we wanted to extend this to higher dimension. The problem would be here the domain is n-dimensional. So if n is greater than 1, h would be in Cn. So dividing by h doesn't make sense. So at least naively, this would not make sense. We should kind of change this a little bit to make sense of this, and it can be done. But let's look at this other definition. This definition we can generalize this to higher dimension in a pretty straightforward way. Suppose we have the function f defined on Cn, or potentially an open subset of Cn to C, right? And we have the points z1 up to zn denoting the coordinates on the domain. Each point z1 up to zn can be written as x1 plus I y1 up to zn can be written as xn plus I yn, right? Now, the same way we define Cauchy-Riemann equations for one variable, we can define them in higher dimensions. So I defined the partial derivative of f with respect to z bar. Previously, we defined this to be 1 over 2 derivative of f with respect to x plus I derivative of f with respect to y, right? When we were working in one dimension. Now we can define partial derivative of f with respect to z1 bar to be 1 over 2 derivative of f with respect to x1 plus I derivative of f with respect to y1. And then we can do this for all variables. We can define partial derivative of f with respect to zn bar to be 1 over 2 derivative of f with respect to xn plus I derivative of f with respect to yn. Okay, so this is just a definition. So let's define this. Now we can have a little slightly more slightly different notation. So for derivative of f with respect to z bar, we used to use the notation d bar of f. This is just a notation, so it's just a notation thing. We can do that here too. So we might use d bar f z1 or z2 up to zn. This simply means partial derivative of f with respect to zj bar. So this bar above partial derivative, in fact, is here over the variable. This is just a notation. Okay, great. So with this notation, we can say what we mean by holomorphic. We can define, so definition, we can say f is holomorphic if the function is differentiable in the real sense or continuously differentiable or smooth in the real sense, smooth in the real sense. So if we think about C and Cn as R to N and R to in the calculus sense, they're differentiable, and all of these partial derivatives with respect to Z1 bar up to Zn bar, they're all equal to 0. So they all vanish at all points in the domain. So previously for us, being holomorphic, it meant that this derivative is 0. Now that we have these derivatives with respect to different variables, we can ask all of them to be equal to 0 for any j between 1 and n. So that would be our definition for a function being holomorphic. It essentially means the function satisfies the Cauchy-Riemann equation with respect to each variable. So derivative of f with respect to zj bar being 0, it means if I write f as u plus iv, where u and v now, u and v are two functions defined on R to n, which is our domain. Our domain is Cn, which can be identified with R to n, or maybe a subset of Cn. If we think about them as two functions to R, now derivative of f with respect to j bar, zj bar being 0, this is the same as saying derivative of u with respect to xj is equal to derivative of v with respect to yj. And derivative of u with respect to yj is equal to negative derivative of v with respect to xj. With the same proof as we have seen before. So being holomorphic now means the function f satisfies the Cauchy-Riemann equations, but with respect to all of these variables, with respect to z1, with respect to z2, up to with respect to zn. If that's the case, then we would say f equals u plus iv is holomorphic. So now we can go and see if this definition is a good definition, if this definition implies the function is differentiable in some complex sense, or if this implies the function f is analytic in some sense. We will be doing that in the next lecture, but before going there, we use slightly different formalism to state the same thing. So for f being holomorphic, for us now, it means derivative of f with respect to zj bar is equal to 0 for any j. Now we just want to state the same thing in very, very slightly different language. We want to use something called complex valued differential forms, differential forms to rewrite the same definition. I want to write the same definition using a slightly different language. The point is that this different language, it just is slightly more convenient and useful when you're working with kind of curved spaces, not just Cn. So not just a flat space like Cn, but spaces which are so-called complex manifolds. They are curved like this sphere. Okay, so I'm going to rewrite this definition in a slightly different language. It might be a little not very convenient in the beginning to work with differential forms, but in long term, they are slightly more they're more invariant in substance. It's easier to use them rather than writing down in coordinates that the derivatives vanish, etc. Okay, so let's do that. Okay, so let's start with this complex differential formalism of a function being holomorphic. Just for simplicity, we start with the real case first. So suppose we have some vector space, say Rn, some vector space Rn, like R2, R3, or etc. There is a notion of tangent space of the vector space, tangent space of Rn at a given point. So let's fix a point. Let's just choose a point in Rn. Let's say this point x1 up to xn is a given point in Rn, right? Let's move this point slightly. Let's say this is a point in Rn. I would say the tangent space of Rn at this given point is just another copy of Rn, at least intuitively, it's another copy of Rn. But rather than being based at the origin, it's centered, the origin of this new one is on the point x1 up to xn. So I call this thing the tangent space of Rn. I denote it with T of Rn at the point x1 up to xn. Okay? The reason it's called tangent space is that when if instead of Rn we have a curved space, so suppose we have a two-dimensional sphere, just like surface of a sphere, we can still pick a point. Let's say I choose a point here. Let's say the point is x. I can think about the tangent space of this sphere at the given point x. It would be a plane tangent to the sphere at this point. It's just a flat thing there. So this is denoted by tangent space of this curved object, which is called S2 at the given point x. Now here, in our case, we are considering only the flat spaces. So it's another space tangent to Rn, but it's centered at this other point x. Right. And because it's flat, it looks as though this space is within Rn itself, but it's just another copy of it. Okay. So this is for me tangent space of Rn at this point x1 up to xn. Okay, great. Now we can think about the basis for this space. So say this is x1, coordinate x1, x2, etc., up to xn. I mean, we cannot show dimensions more than 3, but let's say we have n dimensions, and I'm just denoting them all on this two-dimensional plane. So we have these vectors. We have these unit vectors in direction of x1. We have a unit vector in direction of x2, up to a unit vector in dimension of xn. The notation for these vectors are partial x1. So by this, at this moment, I just mean a unit vector based at this point x1 up to xn, but in the direction of x1. And we do the same thing for the second coordinate, third coordinate, up to n coordinates. So this is partial xn. So we have n unit orthonormal vectors, right? So this vector space has a basis, orthonormal basis, which is partial x1, partial x2, up to partial xn. Okay, this is the basis for this space. Now, whenever we have just a very basic linear algebra, so remembering something from linear algebra, whenever we have a vector space, say real vector space, so whenever we have a vector space, and let's say denoted with V, and this vector space has a basis, so it has a basis, say the basis is E1 up to En, we can define something called dual vector space. So what is the dual vector space? So whenever we have a vector space V, there is another vector space denoted by V star, which is defined as the set of linear maps. So let's denote them by T. Maps from V to the base R, which these are linear. If V is a vector space over R, V star itself is a vector space over R. And if V is, say, n-dimensional, V star is also n-dimensional. And if V has a set of bases E1 up to En, there's a dual basis one can define for V star. So there's dual basis, usually denoted by E1 up to En, but now 1 up to N are superscript rather than subscript. And the way they're defined is that Ej, for any j between 1 and n, when acting on some Ei, is equal to 1 if j is equal to I, and is 0 if j is not equal to I. Right. This set forms a basis for the dual space. Now, going back to our tangent space, so we had our n, and for any point x1 to xn, we define tangent space of Rn centered at x1 up to xn. We can think about the dual space of this space. So it's denoted by T of Rn, x1 up to xn, star. So it's the dual of this space. Sometimes it's denoted by T star of Rn, x1 up to xn, and it's usually called cotangent space of Rn at the point x1 up to xn. Now, Rn, the tangent space of Rn at the given point, as we mentioned, has a basis. We mentioned partial x1 up to partial xn is a basis for Rn at the given point. So the dual basis for the cotangent space is denoted by dx1 up to dxn. So each dxi is an element of cotangent space. So it's a linear map from tangent space at the point x1 up to xn to R. And d of xj, it's defined to be equal to 1 if I is equal to j, and 0, if I is equal to j, and 0 if they are different. The point is that we can extend the notion of tangent space to every point, and therefore these partial x1 up to partial xn and dx1 up to dxn, they can be defined for any x1 to xn. So we usually think about them as globally defined on the whole space. So this is our notion of tangent and cotangent space. Now let's move to the complex setup. So when we have Cn as a real vector space is the same as R to n, right? So let's say this is Cn. We can think about tangent space of Cn at any point. So if I pick a point, Z1 up to Zn, any point inside Cn, I can think about the tangent space of Cn at this given point. But in the correspondence between Cn and R to n, this would correspond to a point x1, y1, x2, y2, up to xn, yn inside R to n. So the tangent space of R to n is centered at this corresponding point, right? So let's say this is a point which is z1 up to zn. If you think about it as Cn, but this is the same as x1, yn as a point inside R2n. And then we are looking at the tangent space of Cn at this point. Now, when I think about the basis of this vector space, I again can say partial x1, partial x2, etc. form a basis. But the point is that now here we are in the real setup, we are denoting our coordinates with x1, y1, x2, y2. So for instance, this would be say partial x1, then the next one would be partial y1, and then partial x2, partial y2, up to x and yn. So in that sense, in a real sense, the tangent space of Cn at the given point has a real basis. So basis is a real vector space, which is partial x1, partial y1, up to partial xn, partial yn, right? So it's a 2n dimensional vector space, 2n dimensional real vector space, so it has 2n elements in spaces. And then, well, we can think about the dual of this space, which would be T star of Cn at this given point. And again, as a real space, it has a dual basis, which is denoted by dx1, dy1, up to dxn, dyn. These objects, they form a basis for this tangent space as a real vector space. So I can think about, say, 5 partial x1 plus 3 partial y3. Or I can think about 2dx1 plus 3dy1, etc. But what if I want to use complex coefficients? What about 5 partial x1 plus I, the imaginary number I, partial y1? This is not an element of the tangent space itself. It's not an element of the tangent space we define. So this is a complex number now. So where does this object live now? So the point is that the first element, this one, is an element of the tangent space at the given point, but the second one is an element of I times tangent space. So if I remove I, the remaining part is in tangent space, but it's not multiplied by I. And the whole thing is the sum of the two elements there. So without making the subject very abstract, I just mentioned this is an element of something called complexification of the vector space, complexification, which we would discuss more in the future. But we can allow such linear combinations. Now, if we do that, then we can look at objects of this form. I can look at partial x1, say plus I partial y1, up to partial xn plus I partial yn, right? And in fact, if we just add a coefficient of 1/2, we define this to be partial z1 bar, up to partial zn bar. And then we also had partial z1. We define this now to be 1/2 partial x1 minus I partial y1, etc. up to partial zn, which is partial xn minus I partial yn. And in the same sense, we can define elements of the complexified cotangent space. So dz1 would be dx1 plus I dy1. And we can define this for any j. And then we have dzj bar, which would be dxj minus I dyj. Right. So now, going back again to the real case, if you had a function f from, say, Rn to R, doesn't have to be a linear function, any, say, differentiable function, there is a notion of exterior derivative of f. So we define exterior derivative of f to be the following. It's denoted by d of f, which is, so it's just a sum. Let's say j goes from 1 to n. It's partial derivative of f with respect to xj. So it's just partial derivative of f times this dxj, the basis of the cotangent space at any point x in Rn. So this is the exterior derivative of a function. This looks a bit formal, but this is actually what appears when we are integrating. Now, in the complex sense, when we have a function from Cn to C, we define something similar. The complex version of this would be the following. So we define d of f to be the sum of partial derivative of f with respect to each complex coordinate zj. We take derivative of f with respect to zj, dzj, plus derivative of f with respect to zj bar, dzj bar, where j goes from 1 to n, right? So that is our definition. Now, if f is holomorphic, where all these derivatives with respect to zj bar, they all vanish, they're all equal to 0, right? So in that case, d of f would be equal to the sum, j goes from 1 to n, derivative of f with respect to zj, dzj. So when you look at expression for f, you don't see any dzj bar. So that would be our definition of holomorphic now. It's something which in the real sense it's smooth, and when you look at its exterior derivative in the complex expansion of variables, in complex variables, there is no dzj bar. You only see dz. So plus no dzj bar here in this expansion, right? So that's just rewriting the same thing using slightly fancier notation. But it turns out this notation will be helpful when we are working with a more advanced, complex setup, more complicated setup. Okay, it's a good place to stop.